Okay, here's what we were talking about last time. We were talking about path independence, and so neat facts that we observed. First of all, this idea of path independence exists. I think it's worth dwelling on that any vector field could have this feature. You're telling me there exist vector fields where it doesn't even matter which path you pick between 2 points. You always get the same answer. All these different curves, infinitely many different curves that start and end at the same point. You always get the same value of the vector field, of the line integral of the vector field. I mean, at a glance, it seems implausible. And then you realize, oh, wait a minute. Kind of, the fundamental theorem of line integrals sort of does that exactly. Right? It's FB minus FA. And you realize, okay, well, that means that all gradients have this feature of being path independent. And I didn't go through the argument, but you can argue the other way. Not only does every gradient have this feature of path independence, but they're the only vector fields that have this feature of path independence. And again, I'm sweeping under the rug more formal issues about regularity and differentiability, continuity, this kind of thing. It's just not, I don't think Math 212 appropriate. So we talked about that. The big ending statement I made was I just wanted to remind you that the reason we're interested in ideas is not because they allow us to do the our eternal goal of computing stuff. Right? It's just not the only thing we're interested in. Computations are not the only thing we're interested in. And so I walk you through this argument here. That's not really computational. Right? This is an application of path independence. The idea of path independence gives rise to the idea, if you trace through the details, it gives rise to the idea of conservation of energy in mechanics. Right? So that's a really important concept, which itself is computationally useful. Right? But path independence in that argument is really not a computational tool, it's a conceptual tool. So that's one of the big reasons why path independence is important. And so that's my counter-argument to the assertion of, path independence doesn't matter. Anytime a vector field is path independent, it's a gradient. I'll just compute with the fundamental theorem of line integrals. Right? That does not allow for making this case. So anyway, all right, so picking up from there. Turns out there's a neat connection to curl. I want to talk about this picture here for the moment. Let me zoom in for focus. Let's talk about this picture. We're going to consider a certain scenario where we have a couple of points, starting point there, ending point there. And I'm going to consider two different curves that start and end at that point, as one might suspect we would if we're talking about path independence. So let's consider that curve oriented that direction, and let's consider this curve oriented that direction. And you're going to be tempted to say that these two curves are oriented the same direction. I'd like to urge y'all to resist this temptation to say these two curves are oriented the same way. The right answer is to say that these two curves both have orientations, but we can't compare them because their orientations are defined in completely different places. You can't say, well, how does the orientation, how does the orientation here, like so, compare to this orientation at that point there, like so? You can't compare whether those are the same or opposite because they're tangent vectors to different curves at different locations. There is no comparison. Right? So resist this urge to call these two orientations the same. If you're not comfortable with that case, let me make the following observation. Let's think about this surface in here. And by the way, this is I'm intending for this picture to be in 3 dimensions. So this surface that you might say is in between these two curves. I mean, there's a lot of different such surfaces, and they could be, bendy and twisty, and likewise the curves could be, bent in a sort of 3-dimensional way, but I have 2-dimensional paper, so, use your imaginations. Okay. So, let's think about how these two pieces of curve relate to the boundary of S. By the way, I'd like to have this surface oriented, I would like to have this surface oriented like so. I'm trying to draw a normal vector that comes out of the page, not into the page. Okay, well, then let's write down, what can I say about, let's see, am I doing this right? Let me make sure I'm doing this consistent with, yeah, okay, cool. So with that choice of orientation, let's write down what is the boundary of S. Harmless exercise, right? The boundary of S. Okay, don't forget the rule. When you say boundary of a surface, boundary means certain conventions, in this case, this being a surface in space, thumb in the direction of the normal vector, swirl in the direction of your right fingers of your right hand, the whole story. And so that means that our boundary of S goes like that, which is C2 minus C1. Well, from this point of view, you're going to want to say that C1 and C2 are oriented in opposite directions because, as part of the boundary of S, C2 is going the right direction and C1 is going the wrong direction. Right? And again, I put those in air quotes. The recording doesn't pick that up, but for your visual purposes, air quotes, right and wrong. You really can't compare the orientations on C1 and C2 because they're orientations of different curves in different places. There is really no comparison. But, in the sense of how they are the boundary of S, the sloppy, the hand-wavy, if you will, point of view is that they're oriented oppositely. On the other hand, let's think about their boundaries. What is the relationship between the boundary of C1 and the boundary of C2? Well, both C1 and C2 start at x0, end at x1, so they have the same orientations on their boundaries. So in terms of their boundaries, there's this lure to call them that they're oriented the same. As part of the boundary of the surface between them, we have this lure to call them opposite. Neither one is right. Neither one is wrong. And in terms of a direct comparison, neither one is right. All right? So don't compare orientations on different curves. One of my points here. All right. Now, so anyway, we have this picture, points x0 and x1, curves C1 and C2, and because they start and end at the same point, they partition off, for example, this surface S, and we have these relationships between the various boundaries. Is everybody on board with the setup so far? Okay. Now I've committed a little sin, so I want to mea culpa before I go on. I claim that this is a victimless crime that I'm guilty of, but I nevertheless do need to confess. I've asserted that when you have two curves, C1 and C2, starting and ending at the same points, that there is at least one surface in between them, as I've drawn here. It's technically not quite always true in free space, because look at this picture, right? If the curves were all tied up in knots, then technically there is, in R3, depending on how you define surface, there is no surface whose boundary is, C2 minus C1. Okay, so the argument that I'm going to make, you could say, has this weakness that it doesn't apply in all cases, such as this nasty one here. What I'm going to say to that is, it turns out that, for the purposes of where I'm going, for the purposes of what I'm going to derive, what I'm going to motivate here, this can be addressed. This can be fixed. I can, so this little road bump, I can finesse this and make this problem go away. I just don't want to have to do that in Math 212. So I'm going to say we're going to ignore this problem, and it's okay. We're still going to get the conclusions that we want. The argument that I'm going to make is still really good intuition for how to think about this kind of stuff. So I want to recognize the problem and ask you to take my word for it that it's not really a problem. Okay. All right. So surface, boundary is the difference of these two curves. These two curves themselves have the same boundary points. All right. Now, with that in mind, let's go down to the next page here and look at I guess I have to zoom back out a notch. Let's look at what does Stokes' curl theorem say. Here it is. There's Stokes' curl theorem, just written down immediately as it applies to some vector field F and this surface S. This surface here, whose boundary is C2 minus C1. And having made that observation, we see that the line integral around the boundary is really the difference of the line integral of C1 and minus the line integral of C2. Okay, so all I've done is write down Stokes' theorem and take advantage of the fact that I know something about that curve. And that gives us that this is equal to this. And it turns out that this one equation, the setup that we have of these two curves and the surface in the middle allows us to draw some really powerful conclusions. And I'm going to walk you through what we can conclude. So let's start with an assumption. Let's say, suppose that the curl is equal to 0. Let's just say, hypothetically. Okay, well now remember, this equation is always true. If the curl is 0, right, if this curl is 0, that means that this flux is 0. That means the left side of this equation is 0. That means the right side of the equation is 0. That means the difference between these two line integrals is 0. That means these two line integrals are the same. That means that no matter what two curves you pick, C1 and C2, as long as they start and end at the same point, this vector field has the feature that you always get the same value of the line integral. That means F is path independent. Right, so that's a pretty awesome conclusion. I mean, I just love this argument because, look, it starts with just a picture. We, set up the picture in a certain way. And we have this powerful connection that comes from just write down Stokes' theorem and follow your nose. When the curl is 0, the vector field is path independent. Really powerful conclusion. Everybody on board? And by the way, the argument turns around backwards just fine. Suppose, let's see if I can erase all this without, okay, there we go. Suppose we know our vector field is path independent. Well, if the vector field is path independent, that means that this is equal to that. That means that this difference is 0. That means the right-hand side of the equation is 0. That means the left-hand side of the equation is 0. That means that this flux of curl, I still don't know what curl is, but the curl is got to be something such that this flux is always 0. No matter what surface you pick, the flux is always 0. What vector field could possibly have this feature that all of its fluxes are always 0 no matter what? Well, there's only one vector field whose flux is always 0, and that is the 0 vector field itself. So not only does curl 0 imply path independent, but path independent implies curl 0. It all comes immediately out of Stokes' curl theorem applied in this geometric situation that I've set up where I have two curves starting and ending at the same point, surface in between, like we discussed. So, pretty darn neato. All right. So I like to append, our previous little diagram. We'd previously discussed how if you have a gradient, that means it's path independent. And we've discussed previously how if it's path independent, that means you have a gradient. Right? We talked about that last time. Well, now we know that path independent means curl is equal to 0, and curl equals 0 means path independent. So what we really have is 3 separate statements, all of which are simultaneous. Any vector field that is a gradient, that's always simultaneous with saying that the vector field is path independent, and that is always simultaneous with saying that the vector field has curl equal to 0. And just a little bit of terminology. The terminology here does get a little bit silly, but keep in mind that curl is a way of measuring how much the fluid is, doing like this, how much the fluid is spinning, rotating, whatever you want to call it, around some sort of an axis. So if the curl is 0, then the fluid is not doing any sort of rotating, and the term is irrotational. Okay, so let me show you how out of hand the terminology this gets. So here's a bunch of terms that all refer to the exact same regularity issues aside, all refer to the exact same vector fields that are gradients. Remember we talked about last time that such are called conservative in connection with the resulting notion of conservation of energy. They're also called, as we just saw, path independent. And they are also called, as we just saw here, irrotational. All right, so this, like I say, it's a little out of hand. So just heads up, right? All of these names refer to different ideas, but different features that all of the exact same vector fields have. So it's not insane that we have all these terms, and yet from your point of view, it's like, well, these all refer to the exact same vector fields. Why do we have to know 4 different names? Okay, so the reason you have to know 4 different names is that all of these 4 different names are in common use in different contexts. And so if you hear the word irrotational, it's your job to think, irrotational, that means the curl is equal to 0, that means it's a gradient. That means it's path independent. Just recognize that all these come for free, yeah.
So is there like any broader definition or like any more in-depth definition of irrotational or just beyond?
Just curl equals 0. I mean, irrotational interpreted directly is this statement, curl equals 0. Now, of course, it happens to be that statement, again, regularity issues aside, is simultaneous with these others. And so there's all these different points of view, right? But the term irrotational itself refers to that property. Yeah, exactly. Okay, so moving along. I'm going to go on now to the next section, surface independence. You might notice the similarity between the title of this section, surface independence, and the title of the last section, path independence. Not a coincidence. So I want to remind you, I'm going to spend a couple of minutes here talking about this diagram. Y'all remember we have this diagram. This is on page, I keep doing that. This is on page 449 of the book. So if you want to flip over to that, feel free. And let me talk a little bit about, I'm going to mark up this diagram in a way to sort of signify all the ideas we talked about in the section on path independence. So we talked first about there are certain kinds of vector fields that have the following property. Whenever you take 2 curves that have the same boundary points, right? A path-independent vector field is a vector field for which, therefore, the line integrals of that vector field over those 2 different curves would always give you the same value. So this is my little cheap representation, loose representation of what it means for a vector field to be path-independent. Now, we also talked about the idea of what it means for a vector field to be a gradient. That's an old idea. And we made the observation that these are simultaneous, right? So the fundamental theorem of line integrals tells us directly that every gradient is path independent. Okay. Finally, we talked about what it means for a vector field to have its curl equal to 0. And we made the observation with this little geometry argument that any vector field that's path independent has curl equal to 0. So we have 3 different properties here, blue, green, and yellow. And what I celebrated back here on the previous page, wherever, here it is that all 3 of those properties are simultaneous. So let's see here. Let me write these down. So green, blue. I'm on the wrong. Where am I? Sorry, I went to the wrong. Let me go back over to here. Yeah. Okay, so green, blue, yellow. These 3 properties as they show up on this diagram, look like that. And they're all any vector field that's blue is also yellow, is also green. Okay. Blue and green are connected by red. Okay, now I wanted to put this down on the diagram because I want to do the following little, dramatic demonstration, which is, you've already seen that ideas that happen, between columns 2 and 3 are extremely analogous to ideas that happen between columns 1 and 2, which are extremely analogous to ideas that happen between columns 0 and 1. We've been ripping ourselves off, reproducing taking an idea, stealing the nut of it, and applying it in a different context multiple times throughout this section. So let's speculate, as a guess, that if we take all of this stuff and just slide it over, that maybe this is true. That's a wild speculation with no justification, right? This is, fingers crossed. We've got a lot of ideas to check here, but maybe it may be that there are some vector fields. Let's see your highlighter. There may be some vector fields such that when you take two surfaces with the same boundary curves, that their fluxes would always be the same. And hey, maybe those vector fields would all be curls of other vector fields. And hey, maybe, yet to be seen, that will be motivated that these are the same vector fields. Curls will have this green feature. Maybe I can motivate that from Stokes' curl theorem. And maybe these vector fields, I'm sorry, I hit the wrong color. Maybe these vector fields that are blue and green might also be yellow. They may have the feature that their divergence is always 0. So this, irresponsibly and with no mathematical justification, we speculate based on hopeful, our wish that the pattern continues. But it gives us a lot of ideas of things to check. And here's the good news. It all works. It's shocking, but it all works. So anyway, this is pretty much the entirety of the ideas that we're going to talk about in this coming section on surface independence. So I just wanted to point out, you can follow along if you have a, copy of the book. If you just keep track of what I've noted here in green, in blue, in yellow. Keep in mind, green, blue, and yellow, they're all the same vector fields, or at least they were over here. Right, they were over here. That all worked. And I'm asserting that this all works. And now I owe you a bunch of explanations, and here we go. Cheat. Let's see. Apparently Stokes' curl theorem is supposed to give us some reason to believe that there is a notion of surface independence and that curls would have that property. Okay. Let's try it. Let's write down Stokes' curl theorem and see if it gives us this idea of, any two surfaces with the same boundary curve and all that business. Okay, so here we go. Here's Stokes' curl theorem. Writing it down naively, optimistically, wishfully, hoping that stuff might work out. Let's consider now two different surfaces. Right? We're going to look at two different surfaces here. Here's one surface. Here's a different surface. Notice I've drawn two different surfaces that have the same boundary curve. Now again, be very, very, very careful with your orientations. There's a temptation to say that, have I oriented these two surfaces the same way, or have I oriented these two surfaces in opposite ways? S1 being oriented like that, S2 being oriented like that. Well, there's a temptation to say that they're the same orientation because they give rise to the same orientation on their boundary. Right? They're both oriented up, you might want to say. right? So, if you play, and I'm going to leave this as an exercise to you guys, but if you do play the thumb game, put your thumb in the direction of the normal vector and right hand, fingers, which way does the swirl, etc. You'll find that these two orientations, as I've assigned them, give the same orientation on the boundary curve. So they're kind of the same in the sense of how their boundaries relate. But now let's think about how they, and let's write that down, by the way. Let me go ahead and write this down. So the boundary of S1 is equal to the boundary of S2. But how do they relate in terms of being part of the boundary of this solid in between them? If there's a solid enclosed between these two surfaces, well, again, we have rules. Got to stick to the rules when we write down a boundary of. Let me do this. Write down boundary of our solid. I didn't give our solid a name. Let me call it R, I guess. The boundary of R is S1 minus S2. And so, again, we have to face up to this seeming, I'm going to air quotes contradiction. It's not a contradiction, right? But this like intuitive unhappiness that we've discovered. If I try to relate the orientations on S1 and S2 in terms of how their boundaries relate, I feel like they're kind of the same. But if I think of how their orientations relate in terms of how they are themselves part of a larger boundary, they're kind of the opposite. So the right answer is, of course, just like with curves, you cannot compare the orientation on S1 and the orientation on S2. They're different surfaces. Their orientations are normal vectors in different places. There is no comparison, really. So be careful with that, right? But that said, make sure you understand how their orientations relate in terms of these, artificial comparisons in terms of how their boundaries are oriented and how they are oriented as part of a larger boundary. All right. So that being set up, notice that if I ask the question of what is the flux of a curl, do like this. What is the flux of a curl through, let's say, the first surface? Well, the flux of a curl through that first surface is going to be a line integral over its boundary curve. What is the flux of the curl through the second surface? Well, Stokes' theorem says it's going to be the line integral over its boundary curve, and these are the same boundary curve. So the flux through S1 and the flux through S2, because we're looking at a curl. Being as we're looking at a curl, we can write down Stokes' theorem. Stokes' theorem says fluxes are computed on the boundary. Because of that, fluxes through S1 are equal to fluxes through S2. And this vector field, this amazing, let's see what color am I going to give it. I guess I'll do this in red momentarily. This vector field, being as it is a curl, has this amazing feature that you can pick any surface you want. You've got to fix the boundary. But other than tying down the boundary of the surface, you can pick any surface you want. Doesn't matter what surface you pick, the flux is always going to be the same because ultimately that flux is going to be computed as a line integral on the fixed, nailed down, agreed upon boundary curve. So this gives rise, as I was suggesting, to this idea of surface independence. We say a vector field is surface independent if you always get the same answer no matter what the surface is. The understanding, of course, that these two surfaces have to have the same boundary curve. Okay. And as we just discussed, all curls have this feature of being surface independent. Okay, so let's go back to our roadmap. We were hoping to be able to flesh this out. We were hoping that we could see a connection between curls and surface independence, that we could make up a notion of surface independence and that curls would relate to surface independence by way of Stokes' curl theorem, and we have now done that. Everybody on board? And I think there's a very healthy exercise in taking the ideas that we've just talked about here and going through and thinking about how they're just a shameless ripoff of ideas that we wrote down last time about path independence. I mean, I literally encourage you to look at the pages like that. Compare. Okay, this path independence over here, surface independence over here. Oh my gosh, they're practically the same idea. Here's another little confession. When I wrote the section on surface independence, I copied and I did this I marked the entire section on path independence at Control C, right? Went down to the next section, Control V, and then I just went through and I literally replaced the word path with the word surface, and I replaced this equation with that equation. I just ripped it off from myself because the correspondence is that strong. And then, of course, I had to make many other little edits, right? But it was easier for me to do it that way than it would have been to type it all over again. Okay. So I think it's lovely. By the way, this does go the other way. This is something I can't give you any justification for here. But not only is every curl surface independent, but every surface independent field is a curl. Again, regularity issues aside, we're not going to talk about, but what if it's not continuous, but what if it's not differentiable? This kind of stuff that I can't get bogged down in that in Math 212. It's things do get weirder if you have regularity issues. So we're not going to go there much. There's one exercise. Okay, so let's capitalize on this. Let's use this. Here's a question. We're given a vector field here, and by the way, we're told that it is the curl of something. A little free information. So we're given a vector field, and we're given a surface that's part of another surface. Blah blah blah. A whole long discussion of the surface. We have a vector field. We have a surface. We want to compute the flux. All right, so now you could take this as a Chapter 5 problem, for sure, right? Chapter 5, parameterize, take a deep breath, plug and chug with the pullback strategy. Okay, that's, look, it's doable. It's doable, right? There's nothing really wrong with that, but it's going to be a little bit tedious, so let's explore other options. I could say, hey, this is the curl of an unknown vector field. I could try to find the anti-curl. Right, and then use Stokes' curl theorem, compute with a line integral. That'd be an option, right? You can come back to our diagram here. If you've been asked to compute a, whoops, come on, color change. If you've been asked to compute a flux of a curl, you could instead compute the corresponding line integral around the boundary of the anti-curl. Here's the problem with that strategy. And you may have noticed at the time when we were talking about Stokes' curl theorem, you notice how I never told you how to compute anti-curls? It turns out it's really hard. So that's just not really on the table either. So that's not an option. Okay, now we were asked to compute a flux. Hey, maybe I can use Gauss's divergence theorem, right? Maybe, why can't I just compute this as a triple integral? Well, I've given you all one example of this as a landmine, tempting but inapplicable idea, which is you always got to check and make sure. If you want to use Gauss's divergence theorem, you'd better make sure that your surface actually is the boundary of some solid. So let's ask that question. Let's go over to this example. Is our surface, let's see here. Okay, so the part of the elliptical paraboloid with that equation, the part of that paraboloid that's above the xy plane. Well, here's a picture of it. The elliptical paraboloid is this whole thing down here. And the part of that surface that's above the plane is just that. That's just not a boundary. So if you were to say, hey, I'm going to apply Gauss's divergence theorem here, the argument fails. There is no surface. This does not enclose anything. Right? Now do be very, very careful to interpret the question correctly, and this is a very common mistake. Students make this mistake all the time. And I think it's just kind of a combination of wishful thinking and carelessness, right? Wishful thinking and sloppiness, however you want to call it. But students look at this and they think, okay, the paraboloid with this equation, and somehow in their minds they kind of conflate the surface with some associated solid. And then they think, oh, if I'm looking at the part above the XY plane, students in their mind are kind of thinking about, well, let's take this whole solid. Oh, wait, it wasn't a solid, it was a surface, and so I'll take this and include this capped off part at the bottom. So a lot of students will think that, oh, look, it is a boundary. Right? It's the boundary of that. Lump, that hill-shaped thing. It's the boundary of that hill. This is absolutely wrong, right? We're looking for points that satisfy two requirements. This surface is points that satisfy that constraint, z equals, blah, blah, blah. And furthermore, that satisfy a second constraint of, the point has to be above the xy plane. Yeah.
Similar to that,
So let me. I'll come right back to you in 2 seconds. Let me just finish this thought. I'll be right back with you. So, points that satisfy both of these constraints, among other things, have to satisfy this constraint. So they have to be on this paraboloid. And these points down here, there's the paraboloid. These points down here are not on our paraboloid, so that's not part of our surface. So this surface it's like an upside down bowl. It is not enclosed. Everybody see what I'm talking about there? Very, very common mistake for students to think that it's enclosed. And it's catastrophic to make this mistake, because then, if you make the mistake of thinking that it's enclosed, well, then it looks like it's a boundary. If it's a boundary, you apply Gauss's divergence theorem, and you get an answer that makes no actual sense at all. Nothing that is part of, if a student writes that down, nothing they've written down is true. And I can feel really bad about it. I feel so sympathetic, and this is why I make a big deal out of this, but I can't give any points because none of it's right in any sense. So it's very dangerous. You remember how I was telling you with symmetry arguments? Make sure you're right, because if you apply a symmetry argument and it's not symmetric, then nothing you've written down is true or relevant. It's a killer. Okay, so anyway, I just wanted to emphasize that point. Go ahead.
Similar to that, if you're in R2 and have asking you the line integral of the upper half of a unit circle, that's not a bounded region either.
That's right. So now the terminology is very important. So she asks about, the upper part of the unit circle. Here's the unit circle. That's called a circle, right? This, when you include the interior, that's called a disk. So be careful with the terminology. Also, if you think about it, if I were to say line integral, let's suppose that you were to interpret it as the upper unit disk. Compute the line integral on the disk. That doesn't make any sense if you think about it. Integrals are computed on curves, not. And you might think, well, I'll just take the boundary, but it didn't say boundary in the question, right? So you got to be very careful with the terminology. And by the way, if you're ever unclear, if you want to come up and ask me during the exam, can you remind me, does circle mean? What's the difference between a circle and a disk? Come up and ask. I will clarify. Yeah. Is that cool?
Mm-hmm.
Okay.
Sorry,
yeah.
my point was a really good question that I was trying to clarify. Is, I know when I think it was in the Green's theorem section, there's some problems where you're asking to compute the line integral of the curve defined by the upper half, or the upper half of the unit circle.
Yeah. So if
similar to that, that's not actually a boundary.
If that,
so a boundary region.
That's right.
You can't use Green's theorem.
You could not use Green's theorem here because that curve is not closed, and so it's not the boundary of any two-dimensional region. And so so this is very analogous. and it's just not a boundary, and so Green's theorem does not apply, just like here, Stokes' theorem, Gauss's theorem just does not apply. Yep, yeah. Okay.
You can close it though, and then
whoa, hey, now you're going to change the question? You can't just change the question.
I mean, and then subtract that line.
Yeah, okay, now, yeah, sure, if you want to, roughly speaking, that's a great idea. What I'm going to show you is even easier than that. Yeah, right. But that's really good thinking, absolutely. Okay. What you can't do is just say, you know what? I'm just going to do that, and nobody saw me do it. You know, we're the perfect crime. I'm just going to stick that in there. That's what you definitely can't do. Okay. And I see that happen on exams. Again, no fair. Okay, so here we go. We have this surface. We're trying to compute a flux through this surface, and now notice we were given a very big hint. We're given that our vector field is a curl. Right, this vector field G is a curl. That means that it's surface independent. And that means, and it almost seems too good to be true, but that means that I can take this surface and I can just throw it out the window because I don't like it. This surface is, look at how the surface is curved. Yeah, it's annoying. Curved things are hard, right? So I can just toss that curve out the window, that surface out the window, and say, you know what I'd like to do instead? I would like to use this surface instead of that surface. Now, notice I said I was very careful when I picked a surface. I picked a surface that has the same boundary, and that is, that's very important. That's part of the deal. I can't just say, oh, I'd like to use, this surface over here. Right? Nope. You can't just change that surface. It's not that independent, right, of surface. You got to pick a surface that has the same boundary curve. But this yellow surface that I've highlighted there, that I called S2, S2 has the exact same boundary, orientation and everything. Exact same boundary as S. So I can throw S out the window and say I want to use S2 instead because of my surface independence. Right? And the S turns into S2 and life becomes a lot easier. Right? Now I don't have to parameterize some paraboloid. Now my parameterization is super easy. It's just, Z equals 0. Nothing to it. So life is good. The normal vector, by the way, you can persuade yourself without too much trouble. Normal vector is really easy to write down. It's just 0, 0, 1. It's a flat surface in the plane, in the xy plane. The normal vector is obvious. Don't even have to parameterize, in other words. There's your normal vector. In fact, even better than that, notice that this dot product turns out to be just xy, and we can make a symmetry argument. This integral is equal to 0. Right? We didn't have to parameterize anything. We make a clever observation. We invoke this very powerful idea of surface independence. Geometric observation about normal vectors. Clever observation about symmetry. And we're done. No double integral. So, anyway, it's a neat trick. Surface independence, very powerful idea. Okay, now let's go back to our thing. So this was our strategy. We were thinking, okay, well, this kind of worked for path independence. Maybe we can talk about surface independence. Maybe it has something to do with curl. And then we saw a connection. Let's see, I'll highlight this in purple. Between surface independence and here, let me slide it back. We saw a relationship between path independence in green and curl being 0 by writing down Stokes' theorem. Here, let me erase the stuff I'm done with. I'm kind of done with that now. Right, we saw a connection between path independence and curl being 0 by writing down Stokes' theorem as applied to this particularly, contrived situation. And it turned out there was a relationship. Every path-independent field has curl equal to 0, and vice versa. So, again, we would reasonably speculate. Maybe that's the wrong word. We can optimistically, with no real reason to expect it's going to work out other than that life has been very good to us recently. Speculate that, hey, maybe surface-independent fields have their divergence equal to 0, and maybe it's because of an argument that I can construct involving Gauss's theorem. Irresponsible, wild speculation. Let's play with it, see if it worked. I mean, maybe it's, who knows, just because it's speculation doesn't mean it's false. We go back to our original picture up here. Remember that we have this setup. We have this solid R. The boundary of R is S1 minus S2. These two different surfaces. These two different surfaces, though, their boundaries are the same as this curve C. So remember this setup here. Notice that for any two surfaces with the same boundary curve, you expect there to be a solid in between. Acknowledged there are issues where the surfaces cross through each other. Again, that all works out. All you have to do is take the, once the surface is crossed through, then the little pieces of solid sort of that are backwards, you just negatively orient them. It's not a problem at all. So this picture, again, I claim is representative. I don't want to deal with the little annoyances. Okay, so representative picture. And let's take that solid R and let's write down Gauss's divergence theorem. There's a straight-up copy of Gauss's divergence theorem. Don't forget that the boundary of R is S1 minus S2. Look familiar? Again, copy-paste. I totally copy-pasted here. So that means that this triple integral is equal to that difference of two fluxes, and let's consider some cases. Let's suppose momentarily what would happen if the divergence is 0. Well, if the divergence is 0, that integrand is 0. That means that this integral is 0. That's the left-hand side of this equation. That means that the right-hand side of the equation is 0. That means that these two fluxes are equal. This is true for any two surfaces that have the same boundary curve. The fluxes are always equal. That means the vector field is surface independent. I mean, the argument is just, it's step by step, perfectly analogous to what we just talked about with path independence. And vice versa. Suppose our vector field is surface independent. Well, that means that these two fluxes are equal. That means that this difference is 0. That's the right-hand side of the equation. That means the left-hand side of the equation is 0. We have a triple integral that's always 0. We have a triple integral that's always 0 no matter what your solid R is. How can you say a triple integral is always 0 for any solid, no matter what your solid is? It must be that the integrand, in this case the divergence, is 0. So the arrow goes both ways. Divergence is 0 means surface independent. Surface independent means divergence is 0. Again, ignoring regularity issues appropriate to this course. Okay, so again, and you notice the patterns in even how I wrote all this stuff down. Surface independent. Let me go back to the diagram where we had all this written down. And let me put this back in here that I just got rid of. Surface independent is simultaneous with being a curl, which is simultaneous with divergence being 0. Everybody on board? All right. strong analogies again. It constantly blows me away that this is the case. So let me go back to the example we just got through doing, and let me sort of, I want to acknowledge there's something kind of weak about this example, a little bit lame, that, how likely is it, come on, in the real world that we're going to be given a vector field and we're just going to somehow know that it's a curl of something. I don't know what it's the curl of, but I know it's the curl of something. Where might this information have come from? Right? It probably, I don't know. This is very manufactured, seemingly unrealistic scenario that this example addresses. So in this next example, I'm going to remove that as this is no longer going to be given free information. I'm going to throw that free information away, and I'm going to do it all over again, taking advantage of these facts here. Okay, so notice in this example, revisited, I have a vector field. No free information about it being a curl. I have a surface that, is the part of the paraboloid, the blah, 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 that's above the blah, blah, blah. The same surface, same discussion. And I want to compute the flux. Now that's very real world. Here's a field. Here's a surface. Give me the flux. No additional free information. So how are we going to decide? I mean, we would like, we'd really like to be able to say surface independent. How are we going to conclude surface independence? Well, we're going to conclude surface independence by asking, that free information's gone, but we're going to ask what else in this diagram would possibly allow me to get what I would like. And what it is divergence. I may not be able to magically induce whether a field has an anti-curl. We don't know how to do that. But I can compute divergence and see if I get 0 or not. Right? So that's all I'm going to do. So here's our vector field. And by the way, at a glance, I can see that the divergence is 0. Can y'all see how I did that? This is a computational little trick. I'm taking the x partial of that. Oh, it has no x's in it. I'm taking the y partial of that. Oh, it has no y's in it. I'm taking the z partial of that. Hey, no z's in it. Right? So at a glance, in this case, you don't always get lucky like this, but every so often. And I love it when stuff works out. So, heads up, be on the lookout for freebies like this. Right? Sometimes at a glance, you can immediately see that the divergence is 0. And therefore, you can immediately conclude that it is surface independent and then proceed just like we did before. Everybody happy? Okay, I have one last little observation I want to make, and that is that I made this case to you about how path independence is really important, despite the fact that it's not really a computational tool. Or said differently, it's kind of a computational tool, but it's a computational tool for which we already have a computational tool, right? If any situation where path independence would be a computational tool, you can use the fundamental theorem of line integrals. Path independence is a second screwdriver in your toolbox. You already had a screwdriver. Yeah, okay, I guess it's kind of a screwdriver also, but how useful is it to have a second flathead screwdriver when you already have a practically identical flathead screwdriver, arguably a better one? It doesn't really buy you that much, right? And then I had to, throwing away that concept, because don't forget, this is a class about ideas. Path independence is very important as an idea. Path independence is the underlying idea, from my point of view, that gives rise to the idea of potential energy, and thus conservation of energy, and thus, one of the big cornerstones of mechanics. It's a big deal, path independence. Not just a computational tool, but I will confess that as a computational tool, you don't really need path independence. You've already got the fundamental theorem of line integrals. That's not true for surface independence. For surface independence, you don't have a previous computational tool, right? Let me go back to the diagram. We say, and again, I want to slide this over. who needs path independence computationally, we can always, if path independence would have applied, we could just apply the fundamental theorem of line integrals. Who needs green? We have blue. Computationally speaking. So, let's, can we say that same thing in this context over here? Who needs surface independence? I could just compute anti-curls and use Stokes' curl theorem. No, we can't. Right? Anti-curls are hard. I haven't shown you how to compute anti-curls. In the vast majority of cases, it's pretty hard to do. So what we have here, from a computational standpoint, path independence is a second flathead screwdriver in your toolbox. Surface independence is your very first ratchet wrench. It's different computational tools, right? You don't have a pre-existing ratchet wrench. So this opens up a whole new computational, opportunities for you that otherwise you just didn't have. So computationally, real cool. Everybody on board? All right. Okay, moving along. So lifetime theorems. By the way, you'd be surprised how close we are to the end of this course. We have 2 sections to go, and we're gonna finish 6.9 today. Because so much of it is just repetition. So I'm going to leave a lot of the examples for y'all to read. I'm going to hit what I think are the important ideas, and everything else are just examples. You can read those on your own. And let me remind you that a lot of the examples that I'm going to skip over here, if you really do want to see those examples, they're on my YouTube channel. You're welcome to take a look there if you want to see those examples explained out. But they're just examples of ideas we've pretty much already talked about. Everything from here on out is really just a matter of, what I'm doing is I'm kind of bringing ideas together that we've already finished. We're basically done with chapter 6, kind of already. Okay. All right, so here's the current state of our diagrams. This is our R2 diagram. Gradient operator, Green's operator. These 2 theorems, right? Here's our R3 diagram. We have these theorems. Come from these operators, all kind of analogous, rip-offs of each other. So there's some additional little things I want to append to this diagram, and that is not just how these operators are analogous to each other, but I want to talk about how these operators interact with each other. And we've actually already kind of done this, but I just want to sort of make the observation and kind of unify them all with one idea. The idea is a metaphor. I made this up. I don't think you're going to hear this or see this anywhere else, but I find it extremely convenient. It's just a metaphor. If you don't like it, you don't have to use it. And I, in fact, would request that you don't cite it. No one's ever heard of it, right? This is me making stuff up. But I think it unifies these ideas really, really well. I think you'll find this really useful as a mental organizational tool, which is why I have a section on it. So I construct this idea of the life cycle of an integrand. I'm going to pretend like our integrands are little not people. That's going to get too dark. But little things. Little semi-living kind of things. All right. The idea is that we're gonna view the application of these operators as being time. It's a metaphor. We're gonna pretend like this is time equals 0, time equals 1, time equals 2, time equals 3. Right? And certainly there's kind of you can take a function, you can compute its gradient. That gradient you can compute its curl. That curl, you can compute its divergence, and it will kind of take you time to do so. So it's not the craziest metaphor ever. Okay. So when you have a thing, time passes, it becomes another thing. Time passes again, it becomes another thing. And you can see the metaphor of the life cycle kind of starting to form. Sometimes you have something. A little time passes. Maybe you get 0. 0 is kind of like, and again, it's just a metaphor. Please don't take this too literally, but it's kind of like death in the sense that it's nothingness, and furthermore, no matter how much more time passes, still dead. Right? So you take the vector field 0, compute its divergence, you get 0. So dead stays dead. Again, that's why I don't want to, these aren't people. I don't want to get too dark, but think of this as kind of 0 is death, if you will. Sometimes if you have a integrand here, let's say a vector field, sometimes, not always, but sometimes that came from something earlier. And I call this survival, right? This thing survived to that point. It survived from here. Okay. It's just a metaphor. Last little bit of the metaphor. Sometimes the thing that's here, that looks like a 0. Sometimes the thing that's here didn't come at all from something previous. It did not survive from somewhere previous. Its little life cycle kind of starts here and goes from there, but it didn't come from earlier. And I call this birth. All right, so this is, here's my first example. Let's see, and I have to zoom out one notch here. Here I have a function that I'm viewing in column 0. I can take the gradient of it. That gives me a vector field in column 1, and then I can take the curl of that. That gives me a vector field in column 2. And what you see is we have something that was born in column 0, it survived to column 1, and then it died in column 2. It's just a metaphor, but does everybody see how my little metaphor works there? Okay. Now let me reveal, why do I like this metaphor? Aside from I have a silly and dark sense of humor. I like this metaphor because it allows for a very crisp and powerful statement that unifies a bunch of ideas that we've talked about, and here is that one crisp and powerful statement. There's one exception, I'll talk about that in a second, but everything has a lifetime of 2. 2. Not 1, not 3. 2. It's a magic number. Everything has a lifetime of 2. Now you'll notice that happened here, right? This thing, this integrand was born in column 0, it died in column 2. It had a lifetime of 2. Now, I claim this is not really new information. You kind of already knew this. We knew that if something was a gradient, that means it's path independent, and something that's path independent has curl equal to 0. So we already knew that something that's born here dies there. So it's not new information. We furthermore already knew that anything whose curl is equal to 0 is irrotational, right? Being irrotational, it's path independent. Being path independent, it is a gradient. So we knew that anything that died here must have been born there. This isn't really news, right? But it is, again, a single sort of succinct way of unifying all these ideas. So I like it for that reason. Again, you don't have to think of it this way if you don't want to, right? But it's kind of handy. So you don't have to think of these results here. So here's 8 statements that all say, different things. You can think of this as 8 separate theorems about, well, if this is equal to 0, then there must exist a such and such. Or if there exists a such and such, then this next thing has to equal to 0. Or always this and never that. I mean, all these statements, they're all different statements, but they all fit. One exception, I'll talk about that in a moment. They all fit with this single statement, which I think is a nice sort of, concept of everything has a lifetime of 2. Okay. All right. So, by the way, I in my little silly metaphor, the world ends here. There is no time beyond that. There is nothing beyond column 3. You can't have a 4-dimensional region inside of 3-dimensional space. Right? It just doesn't make any sense. And so with that idea, if something is born here, it survives to there, and it sort of dies. So there's its lifetime of 2. It doesn't die. The analogy is you gotta work with me on the analogy, right? Okay. Right, so let's talk about that one exception. There is one exception, and this is constant functions. Let's just look at constant functions. Coming back over to our diagram. If you have a function here that is constant, and you take the gradient, you get 0. It's a sad little story. Again, dark, silly sense of humor. Apologize. But this is the one exception. This constant function has a lifetime of 1. That's the only exception, though, to the rule. Within the, again, regularity is very important. We have to, all these vector fields and functions, everything is defined and continuous and differentiable and no irregularity problems at all. It's very, very important for all this stuff to hold. If there is, in your vector field, if there is so much as a single point where the vector field is not defined, then you got to throw all this lifetime theorem stuff out the window. Everything's changed. Everything's different. Y'all are going to have a homework exercise on that that sort of explores that idea a little bit. But other than, with all that regularity assumed, constant functions are the only counterexample, the only exception. Okay. All right. So a couple of quick examples. Oh, by the way, here's how I append our diagrams now. So here's our final completed R2 diagram. We have our players. We have our new operators that we introduced throughout Chapter 6. We have our theorems that came about along with those operators. Those are our, what I like to call our accumulation theorems or our boundary theorems. And these are our lifetime theorems. If you take the gradient of something, then Green's operator is 0. And if Green's operator is 0, then it's a gradient of something. And then etc. likewise down here for our R3 diagram. We're just adding in these lifetime theorems. If you take a curl and then compute the divergence of it, you will get 0. And likewise, if you take the divergence of something and get 0, then it is a curl of something. All right, so I would encourage y'all to dog-ear this page in your copy of the book. This one page sort of encapsulates all of Chapter 6. Sort of. If you had to pick a single page, if you had one page in which to encapsulate as much as you possibly could about Chapter 6, this is a pretty good one. It's hard to beat this. All right, so please take a look at that. By the way, I'd like to encourage y'all to memorize these diagrams. I know that sounds like a lot. Right? Oh my gosh, look at all the symbols there. Let's just focus just on the R3 diagram. Wow, look at all the stuff there. And I'd like to point out that not only is this diagram not that hard to memorize, here's a weird thought. You might have accidentally already memorized it. Because of the patterns, right? Here's what you really have to memorize. You do have to memorize that gradient and curl and divergence appear in that order. That you have to memorize, right? But, that we're computing line integrals and flux integrals and triple integrals, and if we end up with just a point and evaluate with a function, you know how to plug a point into a function. Do you really need to memorize that? We've been doing so much of it. Presumably you've already noticed and memorized that part of it. Again, I don't think you need a reminder of the fact that surfaces have boundaries that are curves. I think you already know that, right? Here's the second thing you need to memorize. You do need to memorize this pattern, right? This pattern that we went through a million times. Sure, you got to memorize that pattern. But again, you may have already memorized that pattern, right? That all these operators are sort of complementary to the boundary and that, this evaluation equals that. I'll bet you've already memorized that, right? And this business about lifetimes, again, you could view that as 4 statements, but they all say everything's got a lifetime of 2. You might have accidentally memorized that as well. So you might even entertain yourself, maybe take out a clean sheet of paper, at some point on your own time, and look at this diagram. Think about, okay, wait a second, what's going on here? What do I need to remember? Then close the book. Put it away, clean sheet of paper, no cheating, and see how much of this you can already reproduce. You might surprise yourself. You might have already memorized it. And if you haven't, I encourage you to memorize the rest because it's so crazy useful. A couple of quick examples. Yes, I know we only have 4 minutes left, so let me choose my examples carefully. Suppose I want to compute a line integral of this vector field, and we want to know, can I use the fundamental theorem of line integrals? Well, you can play the game, try to find an anti-gradient, but let me show you how to save yourself a bunch of time. Can I find an anti-gradient? I've got something given to me here. I would like to know if I can find an anti-gradient. That question is resolved by computing the curl and seeing if you get 0. If you take the curl and get 0, lifetime theorem, it died in column 2, then yes, it must have been born in column 0, and there is an anti-gradient. So just compute the curl. And by the way, this is the little cheat that I've been hinting at throughout chapter 6. You don't have to take a bunch of anti-gradients right off the bat. Just compute the curl and see if you get 0. Let me show you how easy it is to do it, just computationally. Computing the curl, you'll recall, we have this little shortcut. I know I'm going to put x partial there, y partial there, z partial there, and I know I'm going to compute the E1, E2, E3. This is how you do a cross product. Therefore, this is how you compute curl. I don't need to, that's just visual aid. I don't really need that. And then you're going to start computing. So I'm going to need to take the y partial of yz. That's just z. And then subtract the z partial of x squared z. That gives me x squared. In fact, I don't even really need to draw those operators there. I can just remember which is where. I'm going to take the y partial of that, and I'm subtract the z partial of that. In my head, I can see that's z minus x squared. Right? In my head, I can compute. I've already looked at and found that part of the curl. And by the way, I don't even really need to compute anything else. Right? I already can see that this is clearly not going to be 0. I don't know what this is, and I don't know what that is. But it doesn't really matter. This is already not 0. I mean, even if the other two components were to hypothetically both be 0, it's still the case that the vector is not the 0 vector, so we're done. Right? So you can do this too. I mean, you can look at stuff like this. This is how the magic trick works. Look at this thing. Start computing the curl by looking at certain partial derivatives, and as soon as you get not 0, you're done. You know that the curl is not 0, therefore it does not have an anti-gradient. Don't play the game. You're going to lose the game. Anybody see how that works? Okay. All right. There's some really cool physics involved in with the lifetime theorems business. We do not have time to cover this. You're not responsible for it. I'm going to remove it from the syllabus. And I'll send an email about exactly what you're not responsible for there. I do want to spend the last 1 minute here, if I can, talking about one more example. This section, I encourage you to read it. Basically, all the section says is use your diagrams and let the diagram be your guide. So, for example, if you have been asked in a question to compute a flux, don't talk about the fundamental theorem of line integrals. It's got nothing to do with fluxes, right? So what you want to do is ask, hey, is my surface a boundary of something, in which case I can use the Gauss's divergence theorem. Or you want to ask, is my vector field a curl of something, in which that and can I find it? Maybe, maybe not. It depends on the situation. In which case, I can use Stokes' curl theorem. Right? So the diagram, by how it's organized, tells you what your candidates are. It also tells you what to compute. Notice that in both of these cases, whichever one of these theorems you're going to use, if you're computing a flux, compute the divergence. It's going to be your integrand if you use Gauss's theorem. And it's the way of determining with lifetime theorems whether or not there's an anti-curl. So very often, just simply knowing what your goal is tells you what operator should you compute and then what to do with it. Right? And then likewise for if you're computing a line integral, just compute the curl probably. That'll resolve the question of whether there's an anti-gradient. It'll be your integrand if you use the curl theorem. Probably going to be useful calculation. Okay. So I am out of time. So I'm going to leave the rest of these examples for you all to read. So let's see. So we made it. There are all 6.9 is a bunch of examples and this observation about how the diagram sort of brings everything together. So I encourage you to look at these examples. There's like 6 or 7 examples in here. Take a look at these examples. If you want to see the discussions of them, they're on the YouTube channel. And so we are now. I'm going to declare us done with Chapter 6. I owe you an email about the homeworks. They're going to be exercises that I'm going to remove, because we did skip over some topics, especially the physics. By the way, let me in my defense, those topics on physics that I have skipped are topics that don't get covered in the semester Math 212s anyway. So they are supplemental, optional. It's actually totally okay that we skip them. It's not a problem, right? I like to be able to cover them when I can because they're super cool and super valuable. But anyway, I'm gonna send a detailed email about exactly which exercises you should not do. And you had a question?
Yes. So does that mean that since tomorrow's our last day?
Yeah.
Right, so does that mean we give you all the homeworks on exam day?
No. So I'm not going to collect the homeworks for the material that we did today and the material that we'll do tomorrow. Because I don't think it's reasonable. If nothing else, the turnaround time on the grading would be implausible. So those homeworks won't be collected. It's another thing I'll comment on in the email. They are still required in the sense that I assume that you're going to do them. They are part of the learning process. When I'm writing the final exam, I will assume that you have done those exercises. So you still have to do them. They're just not going to be graded. But let me just point out, I mean, if you're thinking, oh, cool, I just won't do it. Let me just point out, homework counts for so little of your grade, right? It's those points that your homework contributes to in terms of the grading of the course are not why you should be doing the homeworks. Right? You should be doing the homeworks because that's what's going to help you do well in the exams. Right? So the fact that that microscopic amount of point value is not going to be there, I hope that won't affect your decision-making process on whether to do it. So anyway, please do those homeworks. Okay, I owe you emails. See y'all. And then all day tomorrow we're going to do optimization. And again, we're going to finish optimization tomorrow. It's going to be fine. Details then. See y'all later.